Multidimensional domains, combinatorial auctions, as opposed to single-dimensional domains, the monotonicity conditions that characterize implementability in multidimensional domains are far more complex. See the discussion in Chapter 9. Hence, designing implementable approximation algorithms is harder. As discussed in the introduction, this chapter examines three aspects of this issue, and in this section we will utilize randomness to overcome the difficulties of implementability in multidimensional domains. We study this for the representative and central problem domain of combinatorial auctions. Combinatorial auctions (CAs) are a central model with a theoretical importance and practical relevance. It generalizes many theoretical algorithmic settings like job, scheduling, and network routing, and is evident in many real-life situations. Chapter 11 is exclusively devoted to CAs, providing a comprehensive discussion on the model and its various computational aspects. Our focus here is different: how to design CAs that are simultaneously computationally efficient and incentive compatible. While each aspect is important on its own, obviously only the integration of the two provides an acceptable solution. Let us shortly restate the essentials. In a CA, we allocate M items, omega, to M players. Players value subsets of items, and Vi of S denotes i's value of a bundle S, which is a subset equals to omega. Valuations additionally satisfy one monotonicity, i.e. Vi of S is less than or equals to Vi of T for S, which is a subset or equals to T. And 2. Normalization, i.e. Vi of empty set equals to 0. In this section, we consider the goal of maximizing the social welfare, find an allocation S1, S2, and so on to Sn that maximizes the summations of Vi of Si summing for all index I. Since a general valuation has size exponential in N and M, the representation issue must be taken into account. Chapter 11 examines two models. In the bidding languages model, the bid of a player represents his valuation in a concise way. For this model, it is hard to approximate the social welfare within a ratio of omega of m to the 1/2 minus epsilon for any epsilon greater than 0, if single-minded bids are allowed. In the query access model, the mechanism iteratively queries the players in the course of computation. For this model, any algorithm with a polynomial communication cannot obtain an approximation ratio of omega of m to the 1/2 minus epsilon for any epsilon greater than 0. These bounds are tight, as there exists a deterministic square root of m approximation with the polynomial computation and the communication. Thus, for the general case, the computational status by itself is well understood. The basic incentives issue is again well understood. With a VCG which requires the exact optimum, we can obtain truthfulness. The two considerations therefore clash if we attempt to use classic techniques, and our aim is to develop a new technique that will combine the two desirable aspects of efficient computation and incentive compatibility. We describe a rather general LP-based technique to convert approximation algorithms to truthful mechanisms by using randomization. Given any algorithm to the general CA problem that outputs a C approximation to the optimal fractional social welfare, one can construct a randomized C approximation mechanism that is truthful in expectation. Thus, the same approximation guarantee is maintained. The construction and proof are described in 3 steps. We first discuss the fractional domain, where we allocate fractions of items. We then show how to move back to the original domain while maintaining truthfulness by using randomization. This uses an interesting decomposition technique, which we then describe.